Hi, cool cats and kittens. Sorry, I was watching too much Tiger King over spring long weekend. Hi, Science2 kiddos. I'm going to use this recording just to quickly review content from chapter 5.9 through 5.11 in Hewitt, all about altitude, range, drag, and satellites. These are kind of the key vocab terms and concepts to take from this. Chapter 5.9 talks about altitude and range, and they are exactly what they sound like. Altitude is the maximum height that a projectile reaches in its parabola path. Range is the total distance that it travels horizontally from where it was launched to where it finally lands. And interesting things happen with these, and if you can understand altitude and range and calculate them, you can make pretty accurate predictions about where things are going to land. And this was relevant during war times when they were firing cannons at each other, and is relevant even for space exploration, firing rockets and trying to figure out where things are going to end up. So you should have done this activity in class, and what you hopefully realized was that when you fire the cannon at these two different angles, as shown in this image here, both projectiles land in the same spot, even though they were launched at different angles. And you should have noticed that for each of these, if you add them up, 25 plus 65, 40 plus 50, 60 plus 90, they always add up to 90 degrees. So, kind of a cool thing to notice that if you have that consistency, then the projectiles always land in the same place. Now, this is conditional on the cannon being level with the ground, though. I tried this with the cannon 5 meters, 10 meters off the ground. This rule doesn't apply then. So, there's that first rule there, that if the angles add up to 90%, it'll land in the same place. It's also interesting to look at what's happening to the actual velocity of the projectile, and whatever it loses on the rise, it gains again on the fall. So you can see that the speeds are consistent. If it's fired at 40 meters per second, then it will be falling at 40 meters per second when it returns to that same level. And same thing up here, it reduces to 30, speeds up to 30 on the way down. And so you see those are always consistent. It's just that here it's rising and slowing down due to gravity, and here it is speeding up. Now, the key thing that you have to remember about all of these examples so far is we are ignoring the influence of the atmosphere and what's called drag from air. And we can't ignore that any longer. So again, second activity you should have done in class was using the PhET simulation to simulate drag. We increased it first, and you should have seen that the here's your original shot right here, this one in the middle. And when we increase the amount of drag, you can see that both the altitude and the range are now much shorter than that first cannonball that was fired, or pumpkin, or whatever it is that you used. Then we decrease the drag coefficient to 0.20, and you'll see that it's the opposite. The altitude is much higher, and the range is much farther than our original shot was. And so you probably, hopefully, surmised this from the activity, but drag tends to decrease these things, right? It decreases both range and altitude. These things do not fly as far as they normally would. And this has limitations in things like athletics, right? Baseball players are constantly fighting against the drag of air. If we were able to play baseball in a vacuum or somewhere where there was no air, I believe the textbook says that the distances that they would achieve with a baseball would be about 6 times what we normally see on Earth. And on that note, I know we had a little exploration of baseball as the do now, and if we launched a baseball at 90% the speed of light. But drag also influences the different types of pitches that pitchers, if you've ever wondered, like, how does a pitcher actually pitch using a, something like a curveball or a fastball, and a curveball is actually when they put a little bit of spin on the baseball. You can see it indicated here. They release the ball in a way that it spins around a little bit, and this actually, rather than having the drag evenly distributed over the ball as it flies through the air, there is a large amount of drag on one end and a small amount on the other. And this, sort of like an airplane wing, causes the ball to follow more of a bent path, right? This would be going very straight, but here, and you can kind of see it here in the deflected wake, that it would be bending a little bit, and that makes it a lot harder for the batter to then predict where the ball is going to be when it approaches the plate, which is why things like a curveball is so effective at striking out batters. Chapter 5.11 looks at fast-moving projectiles, right? So we've got to go a level above a baseball now at this point. The book sort of gives you this information that if something falls for 1 second, it's going to fall for 5 meters. So that's sort of our framework. Just keep that in mind, that you've got 1 second to travel 5 meters downwards. Now, that's your altitude, so to speak. I mean, it's not a little bit different. We're not throwing it up here, but the range can change depending on the amount of force you apply horizontally. It could go even farther. Now again, we're still only falling or traveling for 1 second and only 5 meters down, but we can change how far it goes based on how powerfully we throw it in a horizontal velocity. And so the curvature of the Earth, it turns out that there's a curvature of 5 meters from the horizontal every 8,000 meters. Now what that means is the book does a good job of explaining this, that if you were in a boat on the ocean, here's sort of a primitive looking boat, and 8 kilometers away, or 8,000 meters away, there was another boat on the horizon, that would be actually down here. If it only had a 5 meter mast right there, you wouldn't be able to see it. It would literally be hidden below the curvature of the Earth. You would only see what was maybe above those 5 meters. So kind of a cool thing to think about. But with that in mind, then what if, again, we only have 1 second to travel the 5 meters downward, but what if we were able to actually throw something that would also travel horizontally at 8 kilometers per hour in 1 second? That's the question that I ask here. And the answer is, if you were able to do that, then your projectile would never hit the ground, because the ground would be constantly slanting away as your projectile was also falling back towards the Earth. And so this is sort of a silly picture, but you end up with something achieving orbit. It would just constantly circle around the planet. It is what we call, it has a tangential velocity. That's what we mentioned before, that is high enough to keep it circling around Earth. It is still falling towards the planet, but it is circling around it now. Now, this, though, is unlikely to happen, again, because of the role of air and the drag that it creates. And so, again, think about this. Satellites are anything that achieve that, moving fast enough to fall continuously around Earth. These are things that are in orbit around our planet. And in order to do that, they have to be going at least 8 kilometers per second, which is about 18,000 miles per hour. That's really, really fast. This is why astronauts have to have rockets on their ships. It's not so much to get off the surface of the Earth, they definitely do play a role there, but it's also to get the space shuttle going this fast so that they will stay in space. And that's also why they have apparent weightlessness, right? It's not that there isn't any gravity out there, it's just that they're in free fall around the planet along with their shuttle. You couldn't do this in the atmosphere, right? Traveling that fast in the atmosphere with air would create a lot of friction. It would destroy whatever object was flying through it. But if you go 150 kilometers straight up, you are now outside the atmosphere. There's no more air or gases, that molecules that could be collided with. And so then you would have that orbit motion. And this is what the moon's doing, right? The moon isn't dealing with atmosphere or anything like that. It's just falling continuously around the planet. Same with the ISS, the International Space Station. Again, it is a very common misconception to think that, oh, they're far enough away from Earth that they're not under the same amount of gravity. That is not true. They are satellites, the International Space Station, even the moon, are experiencing very similar levels of gravity to what we are experiencing on the surface of the Earth. It's just that they have that tangential velocity. They're following very, very fast around the planet, right? 8,000 meters per second. And that keeps them from actually ever reaching the ground because it matches Earth's curvature. And then there's a little animation which you can watch on your own to explain that. Thank you.